Log on, tune in, find out. Another good idea from Cambridge.
So our speaker is Shuichi Yokoyama from Tata Institute of Fundamental Research in Bombay. Please.
Thank you. First of all, I'd like to thank the organizer for giving me an opportunity to visit this nice institute and have a 1 hour talk at this cute room. Today's talk will be based on the work in progress, the collaboration with this one, these people, Simon Giombi in perimeter, and Chimi and Seeing in Harvard, and Sachi, Shiraj, Shioman, Niranjan, Sandeep, Spenta in TIFR. Many guys. Okay, and this talk will also be mainly based on this previous paper. Some of them are collaborators. Okay, so let me begin with start discussion with the following question: why are you studying Chern-Simons? Well, Chern-Simons theories appear in the various stages of theoretical physics and play many important role in mathematical physics. For example, Chern-Simons theory is interesting as a pure mathematics, and actually Chern-Simons theories have a close relationship with Noether theory. And in the context of string theory, Chern-Simons theory is also important. For example, action of cubic string field theory looks like Chern-Simons theory, and related it or not, the Chern-Simons theory also appear as an action of open topological string theory, right? In this case, in this context, they consider some wrapping these three branes wrapped on some Lagrangian 3 cycles in the Calumet threefold, and the open string attached on these 3 branes, and such a dynamics open string are determined by Chern-Simons. In the context of M theory, Chern-Simons theory is also quite important because Chern-Simons theories can describe the interaction of the membrane, right? So, which means that Chern-Simons theory is important to construct effective field theory of the membrane. And this Chern-Simons theory is also important as a 3-dimensional conformal field theory because they gives us infinitely many interacting conformal field theories. And also, Chern-Simons theories appear in the context of ADS-CFT correspondence. This Chern-Simons theory can be used as a description of pure gravity in ADS-3. And also, as I mentioned, but related to here, the Chern-Simons theories can be dual CFT3 of ADS4 graph. So they are very, very interesting and appear in the various stages of the high energy physics. So here, let me explain some basic facts of the pure Chern-Simons theories, even though some of you already know. And the action is like this. And as a standard usual gauge theory, this Chern-Simons theory can take the arbitrary gauge group. And in this talk, I will choose gauge group as UN. In this case, the rank of gauge group n is a parameter of the Chern-Simons theories. And here, K is called Chern-Simons coupling constant or level. And this takes an integer value due to the large gauge transformation symmetry of this Chern-Simons. And important point is this action is independent of metric. So this Chern-Simons theory has some topological property, like no propagating degrees of freedom in the back of three manifolds defined on this. And K and N are discretized, so this theory, this parameter are preserved under the RJ flow. So this Chern-Simons theory gives exact CFT and parameterized by K and N. Or we can combine this N and K like this and taking large and large K limit, then this coupling become continuous and this CFT parameterized by continuous line. This lambda is called Tofuft coupling. And this theory is considered to be exactly solvable in full quantum correction, in the sense that the observable like Wilson line are determined by using some by relating the not invariant. Okay, this is a plan of my talk. Next, I will briefly review higher spin theories, and after that, I will talk about application of ADS4 CFT3 correspondence of these higher spin theories to explain my motivation of my study. And next, I will talk about the main topic, the Chern-Simons matter system. First, I will talk about the case which the matter includes only a pure fermion matter case. Next, I will talk about the case which includes boson and fermion in a supersymmetric completion. And I will give a summary and discuss some future work. Okay, let me review some basic aspects of higher spin theory. I have no ability to explain the details. And here I will talk about the free massless higher spin theories. First, I will talk about integer spin case, denoted by phi and mu1 dot mu s. These are totally symmetric. And s is greater than 2, which means higher spin. And curiously, this higher spin field should satisfy this double traceless condition like this to be consistent with higher spin gauge symmetry like this. This is the usual one, but due to this, gauge parameter should satisfy this traceless condition. And this construction can be applied to half integer spin case, denoted by this psi. And in this case, this higher spin field should satisfy so-called triple gamma traceless condition like this. And the gauge transformation is as the usual one, but this gauge parameter should satisfy gamma traceless condition. This is free. Yeah.
So in the former case,
Yes.
you have spin-free field or something,
Yes. Here.
and double trace condition is irrelevant there. Three indices.
Could be.
Spin 2 and 3.
So that would be important to spin 4
I
onwards.
see.
Mhm.
Spin 3 cases.
Okay, thank you.
This is free case, but the non-trivial thing happen here. And it was discovered that the interaction of higher spin can be introduced consistently, which was discovered by Fradkin Vassiliev, 87 and 91, in 4 dimensions first. And after that, such an interaction can be introduced in any dimension. And here, let me mention some remarkable properties of his construction of higher spin theory. First, this higher spin theory is formulated on ADS or digital backward, which is curved backward. Which also means that this higher spin theory doesn't admit flat limit. So some ADS radius may be quantized. And second, this higher spin theory spectrum contains an infinite number of higher spin fields. Which means that one may not truncate infinite number of fields and obtain the finite number of higher spin fields. You cannot. In this.
Spectrum starts from which spin? S equal 2 or 1?
It's 2 or 1.
It's infinite
yes.
power of
Both cases, I think, infinite remaining. Should include infinite remaining.
But I guess the question is starting from the lowest point.
A lower spin. One case is also possible, right?
I don't, I think, you start from the spin 2 and you go up.
You mean 1 is not possible, you said.
I think spin 1.
1, 2, 3, 4.
Added as extra matter.
Mm-hmm.
But if you're looking at a pure theory of higher spin, the things that have been constructed.
Mm-hmm.
So I think that starts from spin 2 and goes higher.
Okay.
But if you want to add some extra matter with spin,
matter.
you would be able to do that.
But here is I do not matter.
Yeah. So then I think it starts from spin.
Okay. Mm-hmm.
And I had one thing to ask you actually. You said that the ADS radius can be, you would, sort of means that ADS radius is quantized.
Mm-hmm.
How do you see that?
I don't know the general discussion, but for example,
are you just saying this because it does not admit a flat space limit?
Mm-hmm. For example, okay, let's suppose ADS3 case.
Yeah.
In such case, first to obtain the higher spin theory, first you rewrite the pure gravity in ADS3 to the Chern-Simons, pure Chern-Simons, with SL2R, SL2R.
Right.
With Chern-Simons coupling given by combination of Newton constant and ADS radius with dimensionless, right? K is given.
Okay.
So K should be quantized, right, by the Chern-Simons from the large gauge, which suggests ADS radius may be quantized.
Shuichi, I'm a little puzzled about, this whole issue, because in 3 dimensions, surely the spectrum can contain a finite number of
it does.
Sure.
So only this statement is only for 4 dimensions.
Yeah, not equal to 3.
Okay.
I think greater than 3.
Yeah, just
greater than 3.
Okay.
all dimensions.
Okay, this property.
Yeah, the second property.
Second property, okay.
But also, I think
Okay.
this I think the 3-dimensional one again, I think it does have a limit
Mm-hmm.
of flat space, if I remember right, because I
Mhm.
I checked once that the Chern-Simons, for higher spin, for example, for spin 3, you just introduce some Chern-Simons, some new kind of Chern-Simons action and take the difference of 2 actions.
Mm-hmm.
And there is a limit of infinite radius. It seems to make sense. So maybe all of these are true only in 4 dimensions.
4 dimension. Oh. Okay.
I mean, the thing that I was asking about is it's not clear that this thing makes sense. Just beyond the classical level, right? Because you would have the mapping being between the V-lines and this usual frame like formalism at the first order and second order formalism. That holds. At the if you just go beyond the this first level, it might not hold. Right. So the quantization, that is why I was asking.
Okay.
If that
So
makes sense.
okay.
The definition of R is probably just a statement that so in ADCFT duality, the tooth clock length is related to the curvature scale, and here lambda is n by k. So n is an integer and k is an integer. So probably.
Okay. Let's discuss. Okay. So let me move on to the application of higher spin to the ADS4 CFT3 correspondent. And crucial conjecture was given by Kuryakov 2002, which states that single sector of three-dimensional free or political ON or UN vector boson model is dual to a higher spin theory in the large n limit. Now, this theory is considered as parity invariant theory with parity even scalar called A-type Vasiliev theory. This parity is defined on ADS4, and now I'm sloppy, but and this conjecture is generalized to the Fermionic case. In this case, singlet sector of three-dimensional free or gross-Nebu type interacting ON UN vector Fermat model is dual to a higher spin theory in the large n limit. And this higher spin theory is now understood as parity invariant theory with parity odd scalar called B-type Vasiliev theory.
What's the reference to the latter version?
I am fine. I try to find, but I don't know the origin of the paper.
So it's some fact that experts know what.
But in this paper they mention in this application. If you know, please. I should cite, but okay. Let me recap the key point of their argument. For this purpose, let me start from the action of scalar field in ADS4, where the mass term of scalar field is tuned like this in such a way that this scalar field has coupled to the background curvature conformally. And by tuning this mass term, you can find two solutions, one of which behaves like Z near the boundary, and the other is Z squared near the boundary. And the point is that these solutions are both normalizable, which means that there are two corresponding CFTs which has the singlet operator with conformal dimension 1 or 2. And it is natural to say that once such a CFTs are free theory, and the conformal dimension 1 case, this maybe correspond to free ON vector boson model, because this singlet operator, single torus operator 5 by 5 is dimension 1, because scalar has dimension half in 3 dimensions. And conformal dimension 2 one is maybe free ON vector Fermat model. This case, single torus operator has dimension 2, because psi has dimension 1 in 3 dimensions. Of course, there's more than this. And by their claim, according to their claim, there are other two CFTs. One is called a critical OM or UN vector boson model, which can be obtained by adding this double trace operator in the free theory and flowing to the IR fixed point, so-called Wilson-Fisher fixed point. And flowing under RG flow, this double trace operator becomes relevant, and this single trace operator has dimension 2. And this is bosonic case, but the fermionic case, the other corresponding CFT is the UV of the Grosnev vector fermion model. In this case, this single trace operator has dimension 1, and after RG flow, this double trace operator is irrelevant in the IR and flow to the free theory dimension half of this single trace operator.
So the fermionic thing goes in the opposite way, you're saying?
Yeah. And these CFTs are corresponding to A-type Barcelona theory with suitably chosen boundary condition. And these CFTs correspond to the B-type Barcelona theory with appropriately chosen boundary condition in ADS 4. This is a summary of the previous page. Now these are parity invariant theory in ADS 4. Now we are in a stage to explain the motivation of my study. We are trying to add this model by adding the Chern-Simons interaction, and we try to more convinced about this conjecture by generalizing the conjecture. This is one of the main motivations of this study. Okay. So let me move on to the Chern-Simons matter system. We use action like this. Here, Chern-Simons terms and adding the free gapless fermion like this. And from this action, you can read off Feynman rule from photon. Here is here, here is here, this one is this, and psi bar A, psi is this. And we take gauge A minus equal to 0, where A minus is A1 plus IA2. By this gauge, this term disappears. So now, with respect to gauge field, action is quadratic. And we want to solve the full quantum effect, which means the classical Feynman rule become fat by the quantum effect, like this. And actually, it is too difficult to solve in the full quantum mechanics. But by taking to fifth limit, actually the situation is drastically simplified. And the gauge propagator reduced to the classical one, and the Feynman vertex is also become classical. And the Feynman propagator is still non-trivial, but anyway, this simplified is very, very helpful to study. And we want to solve this Feynman propagator in the fifth limit, which means n and k goes to infinity with combination fixed. And to solve the fermion propagator, we want to solve this 1pi self-diagram. Can you guess this 1pi diagram? How can you write from this Feynman rule? It is not so difficult. I know, but okay. Okay. The answer is this, so-called rainbow diagram, right? Only this. And now this 1pi self-energy diagram is written by this. So in the equation, this diagram can be written like this, so-called Schwinger-Dyson equation. And the situation is already simplified, so it is not difficult to solve this Schwinger-Dyson equation. The solution is the following, and you can find this 1pi self-energy diagram is 2-loop exact.
You mean in the large two flip?
No, トフという意味。This is just トフ。Okay, let me explain the derivation of effective action. The point is that rewriting the action by using only singlet field. Here I wrote down the same action, and taking a minus equal to 0 gauge, I can find this action is quadratic with respect to gauge field. So we can integrate out gauge field. And resulting action is the following.
Why didn't you do math?
Oh, sorry? Sorry. This should be 0. Thank you for thank you. This should be 0. Sorry. And here, 4 Fermi interaction appear. M is psi over psi, like this. So after integrating out, 4 Fermi interaction appear. And next, introduce auxiliary singlet field to kill 4 Fermi interaction. This part. In order to this, we can choose the action of singlet fields like this. This is for technical reason. I introduced some inverse Green function in 2 momentum space, but anyway, the point is this is chosen in such a way that this auxiliary singlet field can kill the 4 Fermi interaction. And adding this action into the original action, then you can see the quadratic with respect to psi, like this, right? This part disappear. Now this action is quadratic with respect to psi, so you can integrate out psi, like this, right? This part is unchanged, and this part is changed by the Gaussian integration, like this. And here, technically, we use the translation invariant configuration for singlet field sigma. And now, from this, we evaluate by third point approximation to obtain the reading of order large n, reading order large n of large n. And the third point equation looks like this, and this actually is the same as the Schwinger-Dyson equation in the previous page. Okay. I want to understand the system with finite temperature and chemical potential. In this case, yeah, we suspect the more interesting thing happen, but Let me explain. The prescription is the following. To introduce finite temperature, we consider theory on R2 times S1 instead of R3. And circumference of S1 beta is considered as inverse temperature. And we take antiperiodic boundary condition for fermion. And to introduce chemical potential, we turn on the S3 component like this. And this change is equivalent to changing 3 momentum to P3 plus I mu. So the previous calculation is still available by changing these prescription. Schwinger-Dyson equation is like this. And now ground canonical potential, which corresponds to the effective action, is written like this. Actually, we can solve this Schwinger-Dyson equation even though we add chemical potential or finite temperature. And solution is the following. This sigma is, as I said, the 2x2 matrix describing the self energy and looks like this. And F and G here are dimensionless function of P and mu and T. The function is like this. And X is dimensionless parameter, and theta function appear, which is a step function. And finite temperature case is also can be solved like this. And here T is combined like this. PS is absolute value of 2 momentum, R2. Nu is essentially mu. Essentially mu. Precisely divided by T, so that nu is dimensionless. And the solution is parameterized by this C tilde. And this C tilde actually is some curious property. C tilde diverges at lambda equal to 1. And C tilde does not exist when lambda is equal or greater than 1. From this, you can see from this property from this.
You're saying that the solution ceased to exist for lambda larger than 1 or something?
Larger than.
The solution. Theories if C tilde doesn't exist,
Yeah.
you know, partition function, you say the solution doesn't exist. You're saying that there's some pathology of the theory, or?
Yes. This point actually, it's not clear to me, but
I think it's known for the supersymmetry. The ABJ model doesn't exist under these conditions. Right?
I thought that was the condition for supersymmetric vacuum to exist or something.
Okay. You're saying the model doesn't break down. You're asking what is the nature of the breakdown? What breaks down?
Yeah.
I thought in their paper they said that some modes are becoming infinitely massive, decoupled, so you just have no dynamics. So the theory
It becomes trivial
Yeah.
in some way. Would this mean that the partition function is 1? For example, the free energy is 0?
Yeah, I guess.
You're right. Yeah.
It is 0.
They look at the poles in the fermion propagator, and you see 2 of them, and when C tilde goes to 1, the mass goes to 1.
Yeah, summer must becomes infinity in the lambda equal to 1. Yeah.
So that nature should be coming because you should have been using conformality somewhere in the derivation.
Mm. Okay, okay. Maybe, yeah. What you asked is next slide. So, okay. And the ground current potential can be calculated like this. And there are several comments. This ground current potential with scaled by this is monotonical decreases with respect to lambda, and lambda equal to 1, this function is vanishes actually, as you Sunil mentioned. And now we add chemical potential, so this fundamental fermion and anti-fundamental fermion are degeneracy splits like this. And this part is, this corresponds to the Hamiltonian of one particular system. And here is linear dispersion relation. And here is adding the effect of adding chemical potential. And here different sign, right? And if mu goes to 0, this and this are degenerate. And the high temperature behavior of this is the same as the case without chemical potential, but the low temperature behavior is changes like this. And this describes thermal mass as you said, C tilde T. But now we scale by T, so dimensionless parameter here. And we can also compute some momentum distribution. U1 current of this system, and zero temperature case, the behavior is like this. Here you can see the clearly Fermi depending on lambda. And the finite temperature case, this step function is smoothed by temperature like this. This behavior is the same as statistical mechanics usually. Free fermion mode. So system reduced to essentially free fermion. And we can also compute heat capacitance to study the effective degrees of freedom of this system. And heat capacitance looks like this. And you can easily see that this function is decreasing with respect to lambda. And here I change the chemical potential mu to 4, 3, 2, 1 like this. And lambda equal to 1, this heat capacitance C vanishes, which means some degrees of freedom of large N disappear in the lambda equal to 1. So as you said, maybe by thermal mass, degrees of freedom disappear.
Does this mean that there's a phase transition at this point?
Not. If you find phase transition, maybe this function should be not continuous, right?
Yeah, I mean, so that we are higher order phase transition.
At this point.
Yeah.
But
you argue that parity is restored?
I think so. Parity.
So then,
Maybe it's some kind of transition.
yeah.
One side is trivial on the other side.
Oh, okay. If any question.
So the last slide, you were moving from zero temperature to finite, you were plotting
Here is
so your zero temperature is somewhere up
uh,
there, is it?
actually no. The temperature case would be like this. So,
You
maybe-
also have
sorry.
you have a beta and a G there. So
Yes,
I'm
normalized
confused.
by this.
What is beta?
Confused.
Beta is
Beta is
S2 length, S1 length, inverse temperature.
Yeah. And there's also
and there's
temperature.
T.
Maybe both.
T is temperature and N is and pi is
So
pi.
this goes like T squared. I mean one over
T
T
squ-
squared.
Yes, right. Yes, but this this form is okay. Anyway, yeah.
No, I mean, so you, I mean, the thing that I was asking is
Yes.
your zero temperature case would be some sort of a singular. I mean, in this
Here, you mean
in this
here?
place you don't have a zero temperature limit in this case.
Zero temperature limit case, you goes to infinity. So maybe this part is go over maybe this point, but I think this behavior doesn't change. This goes down and disappearing. This is essentially the same to the free energy graph. So free energy graph is actually like this of the zero temperature. So okay, let me move on to the matter includes supersymmetric case. Okay, the action is like this. This is Chern-Simons term, and now as a matter action we add the scalar field boson like this, and psi also, and 4-point interaction appear like this. And here is a 6-point interaction of boson to be, and this action has a conformal symmetry at least classical level. And this action has n equal to 2 supersymmetry if we tune this coefficient as this parameter as 1 or 1. And in this case, this action has Shuichi, and the Shuichi transformation rule is like this. Construction of this is the same as the Abigem case. First, construct n equal to 2 Chern-Simons Lagrangian and matter, and in that case, the auxiliary field, the fields in the vector multiplet become auxiliary field except for gauge field. So integrating out, then you can obtain this. And here I draw all the terms in this Feynman rule from the this you can read off this Feynman rule from the previous action in the previous page. 10 terms 1 AA psi psi phi phi AAA psi bar A psi phi bar A phi phi bar AA phi phi bar phi psi bar psi phi bar psi psi bar phi phi bar phi phi bar phi phi bar phi. And in the as I did in the pure fermionic case, we want to solve this system in the quantum mechanical sense. So these diagrams get quantum correction like this. Or get quantum effect. Do you feel strange? But you can kill this guy by taking m as equal to 0. Right? This guy, get out of this guy. And still messy, but by taking 2/5 limit, these graphs are reduced to tree level, and this guy disappears. But still non-trivial here appear. So to be consider simplify the situation, let me integrate out gauge field. Then the action becomes like this. Now for the remaining things is the fermion propagator and the scalar propagator and the 4 fermion vertex, which are non-symmetric in the fiber phi and the fiber phi. And the 4 scalar vertex is also is not symmetric, fiber phi and fiber phi. And the scalar fermion vertex is the same, and the 6 scalar vertex is also appear, and in such a way that fiber phi and fiber phi and fiber phi are not symmetric. And this vertex is ordered like this. So now let me consider the 1 pi self-energy as we did. Can you guess this from this diagram? 1 pi diagram is the diagram which cannot be split in two by cutting the one single line. Okay. Can you imagine? Yeah. If you imagine, okay. So, okay. Can you imagine? Okay. The answer is maybe this. We have to add at least one vertex. So, and 4 scalar vertex here and here and here exist. So we use 6-point vertex used here, and 4-point vertex here, and 4-point vertex here. And these are not symmetric, so we have to contract like this. And any other term doesn't appear by the reason of the non-planar or such. And the equation corresponding to this diagram is the following, like this. And comment is, if kill this diagram, then this diagram is actually the same as a purely bosonic case. Lambda 4 equal to 0, then this part is the same as a purely bosonic case. Fermion case, maybe you can easily imagine from the previous page. The answer is this. And as the previous page, if you turn off this lambda 4 coupling, x4 equal to 0, then this part is the same as the purely fermionic case. This part. And you can solve this Schrödinger-Dyson equation. And it turns out that actually the solution is the same as the pure boson or pure fermion case. So boson case, this exact propagator reduced to the classical one in the tofu study, which means this 1 pi self-energy diagram vanishes. On the fermion case, the solution is the same, the purely fermionic case, to be exact. Okay, now let me explain effective action. And procedure is actually the same as essentially the same as purely Fermi case. First, I write down the action dividing three parts, only include bosonic term like this. Here only this SF includes only fermionic term like this. Here there is a mixing term like this. And here chi is phi bar phi like, and m is psi bar psi like this. And this F tilde is a coefficient, and these are not symmetric under these variables. Yeah. And let's introduce auxiliary singlet field, alpha denoted by alpha or beta, to keep the interaction terms. For this purpose, we choose the action of auxiliary field like this, and this for boson like this for fermion, and this for mixing term. And you can see here you can kill this term here. And by combining this and this and this, you can kill, you can kill this part. And you can combine this and this, then you can kill this term, like this. And integrating out this singlet field, this action reduced to the original one, right? Because this is auxiliary field, so you can integrate out. Then doesn't affect. And now the resulting action is quadratic phi and psi, so you can integrate out psi and phi by Gaussian integration. The result is the following. Now I change some notation. You change it like this here. And to obtain the leading order of large n, we evaluate this action by saddle point approximation. The result is the following. Okay, this and this looks like the same with respect to this and this in the purely boson or fermionic case. And the saddle point equation is actually the same as the previous one, which derived from the diagrammatic viewpoint. Now we now adding the case discussing chemical potential case or finite temperature case. But now let me stop here.
So can I ask the same
Yes.
question
Okay,
as
sure.
the non-supersymmetric?
Okay.
example? Do you still find some critical behavior at lambda equals to 1 or at any finite value which is equals to supersymmetric theory? Something similar to what Sunil mentioned in this.
Yeah, good question. And that point now we are discussing, and we have results, some results, and if you want, I will discuss after, if time permits. Okay, and okay. Let me make a summary. And we studied UN Chern-Simons theories coupled to vector matter, one complex fermion or one complex boson or supersymmetric case with finite temperature or chemical potential. And we determined several quantities like propagator or free energy exactly in the 2/5 limit, which means full lambda correction in the leading order of large N. In pure fermionic case, the solution does not exist where lambda is greater or equal to 1. And the patch function and the heat capacitance are decreasing with respect to lambda, and the patch function becomes 1 or heat capacitance 0 at lambda equal to 1. Okay, several future works remain. First, refined analysis by including one-over-n correction or adding double trace deformation to obtain the new fixed point in the area. Or you can discuss change the manifold to some curved space S2 times S1 or S3, which was studied by this author recently with different method by taking large F limit. Or we can also do maybe to construct dual higher space array is also another task.
Why do you expect there is a high spin field?
Sorry.
Why do you expect there is a dual higher spin theory to something?
Do you?
Why do you?
Why? So you ask the
I don't see
motivation.
much connection to OM model.
Because connection, you
would expect it. You would expect only field theories which are free, right?
yes.
But now you have added all these matter things in, so you don't really expect to have this. High spin dual anymore, I guess.
Why?
Because of this, the recent results of Maldacena and Zobilev, they show that the only things that can be dual to this alias 4 and higher are free theories, and yours is not a free theory, I guess, right?
But essentially, some. Yeah, not free, but in the taking large n limit.
You're saying you might be able to flow to a free theory.
No, I think the claim of Maldacena et al. Is a bit weaker, right? They want that they say
If their claim is
large n only, or
yeah, it's in the explicit large n limit, it should be free. So here in the explicit large n limit, I don't think your things are free.
I think the result is that a CFT with exact high spin symmetry, you can show that all correlation functions factorize into the free theory.
Yes.
So unless you, for example, break high spin symmetry by finite time effects,
Yeah.
then,
So I'm
you have a chance of having a non-free theory.
right. But here I'm saying, even in the large n here, I don't think it's a free theory, right? With all the matter sectors that have been added in. So why do you expect this dual high spin theory?
Okay, in that point, I'm not sure. I'm still suspect that there maybe some new version of the higher spin theory corresponding to this model. But
Does your theory, part of what they're asking is, does your supersymmetric theory in the large n limit have an infinite number of circuit currents? Yes or no?
Yes.
Which would be,
I would
close
guess
in
not.
itself.
Guess not.
I think you once told in other occasions that even in this Chern-Simons method things, the higher spin currents are conserved up to 1 over n corrections.
Yes, right.
In that sense, it's still
Right. In that sense, yeah.
higher spin currents.
Yes, right.
Would be.
Such higher spin current conservation equation breaks in the next reading.
Yeah,
of-
sure.
so in large n they are conserved.
Yes.
Okay.
Strictly taking n to infinity, then
Okay.
they are preserved.
So you might be actually flowing to something which is
something.
like free theory
Yeah,
in the
something.
large n,
Something.
which is
So the potential free energy behavior essentially is the same as a free, right? With some mass, right? So maybe it's very interesting to construct this dual higher speed theory, if we can, I think. Okay, thank you for your attention.
Question?